Welcome to the Bodhi Academy. My name is Amisha Classo, and in today's video we will continue with our chapter Electrochemistry. So this is the last part of the chapter in which we are going to talk about the applications of this electrochemistry. So previously when we started this chapter, we had talked about two very important applications of electrochemistry. One was electroplating and another was batteries. So now we will look at this application of batteries in detail. So batteries. A battery is an arrangement of electrochemical cells used as an energy source. The basis of an electrochemical cell is an oxidation reduction reaction. So battery, it is an arrangement of an electrochemical cell and that becomes the source of energy. Now this electrochemical cell, it is based on the basis of redox reactions, that is oxidation and reduction reactions. A useful battery should also fulfill the following requirements. So for a battery to be a good one, these three criteria should be followed. First, it should be light and compact so that it can be easily transported. Smaller batteries are more preferable because they are very light and they are very small. In that case, they are easily transportable. It should have reasonably long life both when it is being used and when it is not being used. So it should have a reasonable long life, as in if you have used it for a little while and then it should and then say you have stopped using it, in that case also it should run for a longer time. The next time you use it, it should be in a working conditions. The voltage of the battery should not vary appreciably during its use. Next, when we talk about batteries are also known as cells. So we have two types of major commercial cells, and those two types are firstly primary batteries or cells or secondary batteries or cells. Now let's see what are these primary and this secondary batteries or cells. In primary batteries, the electrode reactions cannot be reversed by an external electrical energy source. So what we are saying, in primary batteries, what happens is that the electrode reactions that occur, okay, they cannot be reversed if we apply an external source of energy. So they are irreversible reactions that occur at the electrode. In these cells, reactions occur only once and after use they become dead. Therefore, they are not chargeable. So what they are saying is that these batteries are the ones, once the reaction is complete, they become dead. In that case, what happens, we can no longer use them. You cannot recharge the battery again. Some common examples are tri-cell and mercury cell. Now if you look at our cell phone batteries, our mobile phone batteries, in that case what has happened, the battery is being recharged. So we can say that they are not primary batteries. Same way, now if you look at the TV remote, those batteries, in that case once they are out of use, they cannot be recharged again. They don't work again even if you try to recharge, or there is no source of rechargeability in them. So therefore they fall under the primary batteries or cells. So secondary batteries, the reactions can be reversed by external electrical energy source. That is, if you have a mobile phone, once your battery is low, what we do, we connect it to an external source of energy from which the reaction gets reversed. Therefore the phone gets charged. Therefore these cells can be recharged by passing electric current and used again and again. So these are also called as storage cells. Now examples of these secondary cells are lead storage battery and nickel cadmium storage cell. About these two batteries we will see ahead. Now let's look at first the primary cell. We have the dry cells and the mercury cell. So let's understand this dry cell first. So if you have to look, this is the image of a primary cell. Okay, so now this is the positive terminal, the other is the negative terminal. This is basically the normal batteries that we use in our TV remotes, AC remotes, all the remotes which we use, in that these batteries are used. Then in between we have the carbon electrode, that is the cathode, and at the sides we have the ammonium chloride electrolyte. So there is some kind of solution that is present, which is the ammonium chloride solution. Then we have a separator that is there. Then there is a zinc casing, that is the anode that is present. then outside we have a protective covering, and then inside we also have a manganese dioxide layer, and at the end we have the negative terminal. Now these are used in torches, toys, flashlights, calculators, tape recorders and many other devices. So now let's look at the construction of this dry cell. This dry cell, it consists of a zinc cylinder. This is filled with a moist paste of NH4Cl and a little of zinc chloride. So this is basically in the form of a paste. Ammonium chloride plus little bit of zinc chloride is present. So the zinc cylinder acts as the anode and the cathode is a graphite. Graphite as in the carbon rod which is present. The carbon rod is surrounded by a black paste of manganese dioxide. So this surrounding, what you see inside is this paste of manganese dioxide and some carbon powder. During use, the zinc case gets consumed and in the end it will develop holes which are responsible for leakage. The leak-proof cells or dry cells have an iron or steel sheet covering the zinc. So now what happens is that at times what we see is that our batteries start to leak. Okay. Now why is that happening? That is during the use, the zinc case which is there. So this zinc case which is there here, this yellow part that you can see, that it develops holes which are responsible for leakage. So what happens in these, there are holes that are formed and therefore it starts to leak out. So therefore the ones which do not leak, they have an extra layer of iron or steel sheet that is covering the zinc. Now let's see how does this dry cell work. So zinc loses electrons and Zn2 plus ions dissolve in the electrolyte. So zinc which is there, it starts to lose its electron and it goes into the electrolyte solution as Zn2 plus. The electrons pass around the external circuit and are taken up at the cathode. So once these electrons are left out into the solution, then they pass through the external circuit, that is the outer circuit, and they reach up to the cathode. This causes discharge of the NH4 plus ions that are present in the ions. So the reactions that take place at the electrodes are, so we have the, at anode we have the zinc that is giving away its electron and it is going as an ion of Zn2 plus. Then at the cathode, the NH4 plus the magnesium which is there plus 2 electrons, they start forming magnesium hydroxide, and we have NH3 that is formed. Then the overall reaction is zinc, then ammonium ion we have, then we have manganese dioxide which gives us Zn2 plus, then manganese hydroxide plus NH3. In the cathode reaction, manganese is reduced from +4 oxidation state to +3 oxidation state. Ammonia is not liberated as a gas, but it combines with some of the Zn2 plus ions and produced from the anode to form a complexation having the formula zinc ammonium Zn NH3 2 plus. So the NH3, that is ammonia, is not actually liberated out as gas, but in then what it does, it goes and combines with zinc, okay, and it forms a complex system of Zn NH3 twice 2 plus. It gives a voltage of approximately 1.2 to 1.5 volts. These dry cells does not have any indefinite life because NH4Cl being acidic, it corrodes the zinc container even when not in use. So one point when we had said that it should be usable even when it is not in use, correct? So what is happening here is that these dry cells, they cannot be used. Why? Because that NHCl, ammonium chloride which is there, it is basically acidic, and what it does is it corrodes the zinc container that is there, and when zinc container that is there even when you are not using the battery. Now let's next look at the mercury cell. So a new type of cell which was found to use in small electrical circuits such as hearing aid, watches and cameras is the mercury cell. Now these mercury cells are the tiny round circular batteries which we get, which usually go into our digital watches. So it consists of a zinc anode and a mercury oxide cathode. the electrolyte is a paste of KOH, that is potassium hydroxide, and zinc oxide. So the reactions occurring in the cell are as follows. So we have zinc plus the OH that combines to give us zinc oxide plus water, and at the cathode we have HgO, that is a mercury oxide, plus H2O plus H2O, and that gives us mercury plus hydroxide. Now this cell has an advantage, that is its potential remains almost constant throughout its life. Now this mercury cells have one major advantage, that the voltage that they give or the potential that they give remains constant throughout the life. There is no change in the potential that occurs. The voltage of mercury cell is approximately 1.35 volts. Now let's move ahead to the secondary cells. Now secondary cells, what we had said, that the electrode reactions which are there, they can be reversed once you connect it to an external source of energy. Now these are some cells which can be recharged. These are called as accumulators, or they are also known as storage cells. These can be recharged and used again and again as a source of electric current. So this is a lead battery. Okay, so this is how a lead battery looks. So if you see the outer thing, it is usually plastic, so that is a protective casing. Then we have a positive terminal, then we have a negative terminal here. We have also these cell dividers which are there. Then we have the positive electrode, that is lead oxide. Okay, so we have these positive, these are like sheets. So we have positive electrodes, that is of lead dioxide, and we have the negative electrode, that is of lead, and it is filled with a solution of dilute sulfuric acid. So now the lead storage cell. Each battery consists of number of voltaic cells connected in series. 3 to 6 such cells are generally combined to get 6 to 12 volt of battery. That's why you see there are those cell dividers and all that are inserted, because it is a compact system of 3 or 6 cells. Now the anode is a grade of lead packed with finely divided spongy lead, and the cathode is a grade of lead packed with lead oxide. So the electrolyte is an aqueous solution of sulfuric acid. At the anode, lead is oxidized to Pb2 plus ions and insoluble PbSO4 is formed. At the cathode, PbO2, it is reduced to Pb2 plus ions and PbSO4 is again formed. So the following reactions take place in the lead storage cell. At anode, the lead which is there, it loses its 2 electrons and is oxidized to Pb2 plus ions. So lead here, it loses 2 electrons and it is oxidized to Pb2 plus. Now this Pb2 plus, it then combines with SO4 2 minus which is there in the solution, and it gives us PbSO4. The overall anode reaction, it goes as lead plus the sulfate ions that are present, giving us lead sulfate plus 2 electrons. Now at the cathode, the PbO2 which is there, it is reduced. So PbO2 plus 4H plus 2 electron, it is reduced to Pb2 plus, and we have water as the byproduct. Now this PbO, that is the PbO2, that is the lead oxide, then again combines with SO4 2 minus to give us PbSO4. So the overall reaction goes as PbO2 H plus plus SO4 2 minus, giving us lead sulfate plus water. Now during the working of the cell, PbSO4 is formed at each electrode. So at both the electrode, what is happening? One common product is being formed, that is PbSO4, and sulfuric acid is used up. So as a result, why sulfuric acid is used up? Because the sulfate ions that are going are from this H2SO4. So as a result, the concentration of H2SO4, it gradually decreases and the density of the solution also decreases. Now, how does these batteries, how are they recharged? Okay, so the cell can be charged by passing electric current of a suitable voltage in the opposite direction. Okay, so this we already know. If we are applying any external voltage, we have to always apply it in the direction opposite to the initial direction. So the electrode reaction gets reversed, As a result, the flow of electron gets reversed and lead is deposited on anode and PbO2 on the cathode. Initially, PbO2 was being deposited on anode and lead was being deposited on cathode. Now the whole reaction reverses. So the density of sulfuric acid also increases. The reaction may be written as PbSO4 plus H2O giving lead plus lead oxide plus H2SO4. When it is used to start the engine of an automobile, it acts as a voltaic cell and it produces an electrical energy. During recharge, it acts as an electrolytic cell. Now next, let's look at this nickel and cadmium storage cell. So this is also a rechargeable cell, but it has a longer life than the lead storage cell, but it is also more expensive than the lead storage battery. However, some of its advantages, because it is smaller and it is comparatively lighter, it can be used in portable and cordless appliances. Now it consists of a cadmium anode and a metal grid containing nickel oxide that acts as the cathode. So here in nickel cadmium we have cadmium at the anode and nickel oxide at the cathode. The electrolyte in the cell is the KOH, that is potassium hydroxide. So the reactions taking place during discharge and charge are, so at anode cadmium plus OH combines to give cadmium oxide plus water. At cathode we have nickel hydroxide which takes up electrons and gives us nickel hydroxide plus hydroxide ions that are given out in the solution. Overall reaction goes as cadmium plus nickel hydroxide giving cadmium oxide plus nickel hydroxide plus water. So the reaction products generally remain sticky to the electrodes and can be reconverted by recharging the cell. So the charging process is similar to that of lead storage battery. So same way you have to apply a external source of energy that will reverse the whole reaction. So the potential that is produced by this cadmium nickel batteries is 1.4 volts. Now let's look at the fuel cells. So these are voltaic cells in which the reactants are continuously supplied to the electrodes. Now in these what is happening is that the electrodes which are there, they are being continuously supplied with some or the other reactants. These are designed to convert energy from combustion of fuels such as hydrogen, carbon monoxide, CH4 etc. directly into electrical energy. So there is no in-between process that is happening. Directly they take combustion of fuels like hydrogen, carbon monoxide, methane and all, and they convert it directly to electrical energy. So in these cells, hydrogen and oxygen are bubbled through a porous carbon electrode into concentrated aqueous sodium hydroxide or potassium hydroxide. Now hydrogen is fed into the anode compartment when it is oxidized. The oxygen is fed into the cathode compartment when it is reduced. So the reactions that occur are, at anode we have the H2 plus OH giving us H2O, and at cathode we have O2 plus H2O giving us hydroxide ions. So overall reaction goes as H2 plus O2 giving us water. Now each electrode, it is made up of porous compressed carbon that contains a very small amount of catalyst of platinum, silver and COO, that is cobalt oxide. Now these fuels are more efficient than conventionally used methods of generating electricity on large scale by burning hydrogen carbon fuels, because these fuels convert the energy of fuel directly into electricity. Okay, so that was it for this chapter of electrochemistry. In the next video we will solve the overall problems that are related to this chapter, and then we will finish this chapter. So that was it for today's video. Please don't forget to like, share and subscribe to the Bodhi Academy.